Okay, now let us come to see the problem sections. Here, if you see some examples on this Liebnitz test, discuss the convergence of the series 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus and so on. Now here the solution of this says that if this is a series and the Leibniz test says that if your series minus 1 to the power of n minus 1 of an, where n running from 1 to infinity, is satisfies the condition an plus 1 less than an is a one condition, and the another condition is the limit n tends to infinity of an is equal to 0, then this series is convergent. Now therefore let us see whether this series satisfies these two conditions. Now if I write this as in this form, and this series will be in summation n from 1 to infinity minus 1 to the power of n minus 1 and 1 by n. As n running from 1 to infinity, you can get the same series. Therefore here it is an alternating series. It is an alternating series, and in this alternating series our an term is a positive. Our an term is positive, and this an will be 1 by n, and 1 by n plus 1 will be our a of n plus 1, and this an and an plus 1 satisfies the first conditions. What is that first condition? See this, 1 by 2 is less than 1, 1 by 3 is less than 1 by 2, 1 by 4 is less than 1 by 4. Therefore the given series satisfies the first condition, that is our an plus 1 less than an. As this satisfies the first condition, we need to check the second conditions of the Liebnitz test. What is the second conditions of the Liebnitz test? It is the limit of the nth term. The limit of the nth term should be is equal to 0. Here the limit of an as n tends to infinity is equal to what? This is equal to limit n tends to infinity 1 by n. As n tends to infinity, it will be 1 by infinity and is a 0. Therefore it satisfies the first condition and the second conditions of the Liebnitz test. Therefore by Liebnitz test, the given series is convergent. Similarly, we can see the another one here to the second one. If this is the first one, to the second one, it says that discuss the convergence of the series 1 by 1 3 minus 1 by 2.4 plus 1 by 3.5 minus 1 by 4.6 plus and so on. And this series can be written as summation n from 1 to infinity minus 1 to the power of n minus 1 divided by n into n plus 1. If this is n plus 1, n plus 2, sorry, this is 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5. Therefore its nth term will be equal to this, and this denotes our an. This denotes our an. And here we can easily see that as 1 is 1 by 2 is less than 1 by 1 and 1 by 4 is less than 1 by 3, we can say that 1 by n plus 1 is less than 1 by n and 1 by n plus 3 is less than 1 by n plus 2 for all n. Therefore it together satisfies the first condition of Liebnitz test. And to check whether this satisfies the second conditions of the Liebnitz test, it says that the limit n tends to infinity of an is equal to 1 by n, limit n tends to infinity 1 by n into n plus 1. Again, for this as n tends to infinity, this will be 0. Therefore, by the Liebnitz test, we can say that the series is convergent. Now, let us look at the next problem. Here, this is to test the convergence of the series 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 plus and so on. And here, how will be our nth term of this series? In this series can be written as summation n from 1 to infinity minus 1 to the power of n minus 1 divided by 2n minus 1. If you want, you can get this by the 1, 3, 5, 7. This is what your formula to find the nth term a plus n minus 1 into t. By using this, you can get the 2n minus 1. Therefore, if this is our series, we need to check whether this series satisfies those two conditions of the Liebnitz test. If this series satisfies those two Liebnitz test conditions, then we can say that this series is a convergent. Hence, it is alternating series. Obviously, it is an alternating series. And whether this satisfies the conditions, okay. And our an is again 1 by 2n minus 1. Here, as it is n is running from 1 to infinity, this is more than 0 for all n, and it is said that here 1 by 2n plus 1. And what is our an plus 1 is, our an plus 1 will be 1 by 2n plus 1. 1 by 2n plus 1. We need to add two numbers to this one. Now, this is less than this one. That is, an plus 1 is less than an. It satisfies. Hence, since an plus 1 is less than an, hence first condition of Liebnitz test is satisfied. Now, to check the second condition, that is the limit of n tends to infinity is equal to limit n tends to infinity of 1 by 2n minus 1. And here again, as n tends to infinity, this term will be 1 by infinity, therefore it will be equal to 0. Hence the limit of an as n tends to infinity is 0. Therefore by Liebnitz test, the series is convergent. By Liebnitz test, the series is convergent. Now similarly we can continue with all the problems. Now let us have a look at the another problem, and the problem of the another one is like this. Fourth one, test the convergence of the series 1 minus 1 by 2 power 3, 1 plus 2 plus 1 by 3 power 3, 1 plus 2 plus 3 minus 1 by 4 power 3, 1 plus 2 plus 3 plus 4, and so on. Now here what is our nth term is, if you look at this is the first one and this is the second one, second to the power of 3 and 1 plus 2. Next third term 3 power t 1 2 3, 4 power 3 1 2 3 4. Therefore our nth term of the series will be from 1 to infinity, and it is an alternating series, therefore it is minus 1 to the power of n minus 1. And this is in the denominator, what we have is n power 3 is, therefore in the denominator n power 3, and in the numerator this is up to the n value 1 plus 2 plus 3 plus so on up to the n. And here what is the formula for this? This is the sum of the first natural number, and we know that the formula of the sum of the first natural number is n into n plus 1 divided by 2. Therefore this will be summation n from 1 to infinity minus 1 to the power of n minus 1, and this is what n into n plus 1 divided by 2 and n cube. By cancelling this 2, your series will be n from 1 to infinity minus 1 to the power of n, and this n plus 1 divided by 2n square, and therefore it is a alternating series. Here our an is equal to n plus 1 divided by 2n square, and this is obviously greater than 0 for all n, and our an plus 1 is equal to n plus 2 divided by 2 times of n plus 1 square. And here if we take v is equal to 1 by n, if we take v is equal to 1 by n, then the summation of vn as n tends to 1 to infinity will be equal to 1 by n is divergent by p series that we know. And here what is our an minus an plus 1 is, an minus an plus 1 will be equal to n plus 1 divided by 2n square minus n plus 2 divided by 2 times the n plus 1 whole square, and this is nothing but n plus 1 whole cube minus n square n plus 2 divided by 2n square n plus 1 whole square, and this is again equal to n square plus 3n plus 1 divided by 2n square n plus 1 whole square, and this is obviously greater than 0 for all n. Therefore it implies our an greater than an plus 1 for all n, means it satisfies the first condition. It satisfies the first condition. And again to check the second condition, that is the limit of an as n tends to infinity, it is equal to limit n tends to infinity n plus 1 divided by 2n square. 2n square is equal to limit n tends to infinity 1 by 2 into 1 by n plus 1 by n square. Now the limit of an is equal to 0, because it is also 0, it is also 0, so therefore it is 0. That is, your limit n tends to infinity equal to 0, it satisfies the Liebnitz test. Therefore by Liebnitz test the series is convergent.